Hello. In today's video, I'd like to examine the relationship between Q of a parallel resonant circuit and the bandwidth of such a circuit. And quite often it's referred to that the Q, of course, is the relationship of the stored energy to the dissipated energy within a circuit. But also an important relationship is that the Q is related to the bandwidth that a circuit will have, namely the ratio of the center frequency or the resonant frequency of the circuit and the bandwidth. Now, the bandwidth we define as the 3 dB bandwidth, or where the amplitude falls by half in terms of power. And we'll see how that becomes convenient in just a moment. Now, on this worksheet, I have reproduced a plot for the parallel resonant circuit shown here with a parallel capacitor or shunt capacitor and shunt inductor, and they're connected to conductances. And what we're plotting is the magnitude of the susceptance for the inductor, and that's shown in orange. So this is the magnitude of the susceptance for the inductor, and the magnitude decreases with increasing frequency. And this is once again a susceptance, which is 1 over reactance. And in the same vein, the susceptance of the capacitor increases with frequency, the magnitude of the susceptance. And when the two are combined in the shunt circuit shown here, their combined magnitude is plotted in green. And what we're actually plotting is, since they have opposite signs, it's going to be the difference between the two magnitudes. So the two magnitudes. But then, since after resonance, their relative magnitudes, one becomes greater than the other, and they swap after resonance. So what we're plotting really is the absolute value of that difference between the two when they're combined. So in green, we have the absolute value of the magnitude of the combination of the inductor and the capacitor. And you can clearly see that at a certain frequency, they cancel each other out, and that's where you have resonance. But what we're interested in today is the bandwidth, the 3 dB bandwidth for an overall circuit. And so what we've also plotted is just the constant value with frequency of the conductance, the combined conductance of the circuit. So in red, we're showing the magnitude of the conductance. Now, when we define the bandwidth as the 3 dB bandwidth, that's where, like we said, the amplitude drops by a half of the signal power. And what that implies is that half of the power is getting through or being delivered to the conductance, and the other half is being absorbed and stored by the susceptance. So what that implies is that the magnitude of the combined susceptance and the magnitude of the conductance are the same. So BL that combination, the absolute value of it, is going to be equal to the magnitude of the conductance. And where that happens on this graph is from the lower frequency where they intersect to the upper frequency where they intersect will be, that spread is the bandwidth, the 3 dB bandwidth of this resonant circuit. So graphically, we can see, based on the shape of the plot and the relationship of Q being the ratio of the susceptance to the conductance, if we increase the conductance, Q will be smaller. And that also implies with a lower Q, lower value of Q, the bandwidth will be larger. So if the magnitude of the conductance goes up, we can draw that here. And hopefully the computer will straighten out this line that I draw. It did. Increasing the conductance graphically, we can see that the bandwidth, or the points where the two lines intersect, become further apart. Graphically, the bandwidth is larger. What we'd like to do is examine a mathematical or algebraic relationship that demonstrates the same concept. So we've seen graphically that when the conductance is increased, the Q value decreases and the bandwidth increases. But we'd like to kind of nail down that relationship between the bandwidth and Q a little bit, examine that in a little bit more detail mathematically. We can look at that here. But this the foundation of looking at this is the observation that for a 3 dB bandwidth, the susceptance and conductance magnitudes will be the same. So we can use that as our starting point. Okay, so after a tiny bit of cleanup here, let's just review that the susceptance of an inductor is 1 over omega L, and the susceptance of a capacitor is just omega C. And we're going to look at the figuring out the bandwidth in a mathematical sense. We're going to look at the two different frequencies. Let's call the lower frequency 3 dB point omega 1, and we'll call the upper one omega 2. Since we're looking at the absolute value of the difference in magnitudes of the susceptances, we can arrange the terms so we end up with a positive result, so we don't have to do negation. And below resonance, at omega 1, on the low side of resonance frequency-wise, we see that the orange line is greater magnitude, so the inductor susceptance is larger than the capacitor susceptance. So we'll put that term first. So we'll do, for omega 1, we can say 1 over omega L minus omega C. That difference, that combination, since they have opposite signs that are going to detract from each other, so we're reproducing that green trace, and at the lower 3 dB point, that magnitude is going to be equal to G. Now at the upper 3 dB point, the magnitudes of the susceptances have flipped, so the capacitive susceptance is larger. So in order to maintain sort of that absolute value for omega 2, we'll switch the order of the terms. And like I said, this is because we're looking at the absolute value. Now I could achieve the same result with negation, but I'm just looking at the graph and seeing the relative sizes of the magnitudes, and I'm just arranging the terms to end up with a positive result, since my desired outcome is the absolute value. Okay, so now what we can do is solve for omega, because we want to come up with a term for the bandwidth. And let me just write down the bandwidth is going to be bandwidth. I'll use a 2-letter BW to represent the bandwidth. It's the upper frequency minus the lower frequency. And we're talking in terms of omega because we've got these susceptances. So it's omega 2 minus omega 1. And then to convert to frequency, we divide by 2 pi. Okay, so now we can solve for omega. Let's start out on the lower frequency, omega 1. We can combine terms here. So we could say 1 minus omega squared LC equals G. And then kind of move the terms around. Okay, so further expanding, this becomes LC omega squared plus LG omega minus 1 equals 0. And now we can use the quadratic formula to solve for omega. And we're solving for omega 1, so I'll put that subscript back in. So omega 1, and let me just paste the quadratic formula for reference. Minus b plus or minus b squared minus 4ac. If we use the minus term, we'll get a negative frequency, so we'll discard that result. But substituting in a, b, and c here, the square term is a, the linear term is b, and the constant term is c. So minus b, so we get minus LG plus the square root of b squared LC squared, b squared. So that's LG squared minus 4a, and c is minus 1. And that's all over 2a, 2LC. So expanding a little bit further, we can get minus LG over 2LC plus the square root of, we'll put the denominator into the radical, so we get LG squared over 4 LC squared minus, and then with the minus 1 factor, that flips the sign, 4 LC over 4 LC squared. Okay, so that's omega 1. And we'll stop there as far as algebraic manipulations. Now let's do the same thing for omega 2. Omega squared LC minus 1 over omega L equals G. Expanding that, we get LC omega squared minus LG omega minus 1 equals 0. And so when we plug it into the quadratic equation, we get omega 2 equals LG plus square root of minus LG squared minus 4 LC times minus 1 over 2LC. And we can just sort of partially, we can go to the same step that we did before. So we get LG over 2LC plus the square root of LG squared over 4LC squared plus 4LC over 4LC squared. Now, what's neat about this is that that messy stuff that's under the radicals, since we're interested in the bandwidth, recall up here that the bandwidth is omega 2 minus omega 1 over 2 pi. And everything's the same except for the sign on the first term between the two, omega 2 and omega 1. So when we subtract omega 2 minus omega 1, these terms cancel, they subtract from each other, and we end up with 2LG. So omega 2 minus omega 1, 2LG over 2LC, or simply G over C. So the bandwidth is omega 2 minus omega 1 over 2 pi. So the bandwidth is omega 2 minus omega 1 over 2 pi, which equals G over 2 pi C. And I'll just write it down. The inverse of the bandwidth, or 1 over bandwidth, equals 2 pi C over G. That's just taking the inverse. Okay, so now Q, as you recall, is the susceptance over the conductance. And for the capacitor, the susceptance is omega, and at resonance, it's omega naught C. So that's the susceptance, and you have the conductance. So that's the Q in terms of the capacitance. And that, in terms of frequency, is 2 pi F naught C over G. Well, comparing the bandwidth and the Q in terms of the capacitor, we see that we have all the terms for bandwidth. The only extra term is the F naught. So we can substitute in the bandwidth, and we end up with the resonant frequency divided by the bandwidth. So we arrived at algebraic quasi-derivation of that relationship between the 3 dB bandwidth and Q by comparing the magnitudes of setting the magnitudes of the susceptance and conductance to be equal, and then solving for frequencies, the band edge frequencies, using the quadratic equation. And then the bandwidth is the difference between the upper and the lower frequencies. So we did a bit of algebraic manipulation, and we actually got to that formula of the resonant frequency ratioed to the bandwidth. So that's what it looks like algebraically, and graphically it makes sense if you look at the plot and the points where, going back to the plot, the points where the magnitudes are equal. Okay, so I hope this was useful to examine that relationship a little bit more closely. It's usually just presented and assumed that it's obvious, intuitively obvious, but I found it quite significant a relationship and worthy of a little bit more explanation, examination, let's say. And fortunately, that text that I mentioned had a discussion about it, and I thought I'd share it with you here, together with some additional graphs. Again, I hope it was helpful, and we'll see you in the next video. Thank you.